Hello, my name is Andrei Kulikov, and in this video I'd like to make an experiment on multi-class classification task and talk about it. So the task is the following. I have a data set with some consistency of classes and the type of them. There are seven types from 1 to 7. I want to make a model that will definite the type on this on some data on some data. So I do it on Kaggle. Here is the starting code. Here is the code for plotting. Here I load the data set and I see it can be done, so no point. I see that the following thing. I see that the values of the columns differs, so I certainly have to do some where is it, normalization. Also I see the target value. So I have type, I make a type as a target, and I see that it is from 1 to 7, and also I see that there is no 4 and some information about the data set. For multi-class task, I have to make one hot encoding. I'll do it later, but first of all I'll do the following thing. Yes, it is going. I'll divide my data set on train and valid data sets with this percentage. Then I make scaling from 0 to 1. It works in my case without this, but I do it because it must be done. Now I see that all the values are from 0 to 1. Okay, it's fine. Then I make my target value as to categorical transformation. It became in such a variant. So yes, I see that 2, 3, yes, before it was 2, but now it is 0, 0, 1, 0, 0, 0, 0, 0. And some other tests the same. Okay, what is the shape? I shall need this value to make the input shape for my Keras sequential model. It is yes. Then to these neurons will come the data. Yes, the data. Sorry. In my model settings appears batch normalization. What is it? Batch normalization or batch run can help correct training that is slow or unstable. With neural networks, it is generally a good idea to put all of your data on a common scale. The reason is that stochastic gradient descent will shift the network weights in proportion to how large an activation the data produces. Features that tend to produce activations of very different sizes can make for unstable training behavior. Now, if it is good to normalize the data before it goes into the network, maybe also normalizing inside the network would be better. In fact, we have a special kind of layer that can do this. The batch normalization layer. A batch normalization layer looks at each batch as it comes in, first normalizing the batch with its own mean and standard deviation. Then also putting the data on a new scale with two trainable rescaling parameters. Batch norm in effect performs a kind of coordinated rescaling of its inputs. Okay, fine. Then I put the capacity here. What is capacity? A model capacity refers to the size and complexity of the patterns it is able to learn. For neural networks, this will largely be determined by how many neurons it has and how they are connected together. So capacity is here. Here is the capacity. If it appears that your network is underfitting the data, you should try increasing its capacity. Oh, sorry. Let me think. Sorry. Okay. Adding. You can increase the capacity of a network either by making it wider, more units to existing layers, or by making it deeper, adding more layers. Wider networks have an easier time learning more linear relationships, while deeper networks prefer more non-linear ones. Which is better just depends on the data set. Hard to understand, but here is okay. Here is wider example, and here is deeper example, more layers, and here is more nodes. Yes. Okay. Yes. Activation. So also we use here activation function. Here is relu, and here is softmax that is used for multiclass classification task. Sorry. Multiclass. What is activation function? Here it activates a result of the neuron. So dropout. Yes, we use. 1 second, please. So dropout. It can help correct overfitting. We randomly drop out some fraction of a layer's input units every step of training, making it much harder for the network to learn those spurious patterns in the training data. Instead, it has to search for broad general patterns whose weight patterns tend to be more robust. Wonderful. So I put the dropout. Sorry. The dropout here with some rate. And then I compile my model with the optimizer and the loss function. So about optimizer, they have described the problem we want the network to solve, but now we need to say how to solve it. This is the job of the optimizer. The optimizer is an algorithm that adjusts the weights to minimize the loss. Virtually all of the optimization algorithms used in deep learning belong to a family called stochastic gradient descent. They are iterative algorithms that train a network in steps. One step of training goes like this. Sample some training data and run it through the network to make predictions. Measure the loss between the predictions and the true values. Finally, adjust the weights in a direction that makes the loss smaller. Simple. They just do this over and over until the loss is as small as you like, or until it won't decrease any further. So learning. So I put the categorical cross entropy loss function when there are two or more label classes. Okay, I tested with this parameter, it also worked. Wonderful. And put the metrics here. What else I have? I have learning rate and batch size. Okay, so here I will use early stopping and put here the batch size and the number of epochs. So some words about this. Am I running? Yes. Learning rate and batch size. Notice, please, that the learning process only makes a small shift in the direction of each batch instead of moving all the way. The size of these shifts is determined by the learning rate. A smaller learning rate means the network needs to see more mini batches before its weights converge to their best values. Smaller learning rate means the network needs to see more many batches before its weights converge to the best values. More. It is very complex for me. The learning rate and the size of the mini batches are the two parameters that have the largest effect on how the SGD training proceeds. The interaction is often subtle and the right choice for these parameters isn't always obvious. Yes. Fortunately for most work, it won't be necessary to do an extensive hyperparameter research to get satisfactory results. ADAM is an SGD algorithm that has an adaptive learning rate that makes it suitable for most problems without any parameter tuning. So use ADAM, don't think about learning rate. ADAM is a great general purpose optimizer. So about underfitting and overfitting, these topics are used hardly in AWS exam for machine learning. I passed it a year ago, and now I'm repeating this, but it's like a surprise again and again. So underfitting and overfitting. There can be two problems that occur when training a model: not enough signal or too much noise. Signal is useful information, and the noise is not useful, or some out of range information, or some rare information. So underfitting the training set is when not information data is when the loss is not as low as it could be because the model hasn't learned enough signal. Overfitting the training set is when the loss is not as low as it could be because the model learned too much noise. The trick to training deep learning models is finding the best balance between the two. For that is used the dropout, the batch size, the learning rate, parameters, and also early stopping. When a model is too eagerly learning noise, the validation loss may start to increase during training. To prevent this, we can simply stop the training whenever it seems the validation loss isn't decreasing anymore. Interrupting the training this way is called early stopping, but it's not the only method for stopping overfitting or underfitting. Okay, okay. So I started here my training. Sorry. Start from the beginning, and what I see. I see bad result. Bad result. So I see that the validation accuracy is this value, and it is very small. So I made some experiments with this, uh, with this, and this, and this, and it didn't help me. The maximum value was 0.6, and of course here is my training loss and here is my validation loss. So the results will be not as they must be, and the accuracy differs deeply. So if I test, I have a testing small data set. I'll better open it in Excel. Yes. Why? 1 second. Sorry. A small data set of 11 parameters, and here is its targets: 1, 2, 3, 3, 5, 6, 6, 6, and 7, 7. I should get these numbers, but I got here something different from the task. So why did it happen? It happened because the data set is very small. Even in AWS SageMaker, when I made some experiments a year ago before some problems in payments in Russia, it refused me to use the dataset with the amount of rows less than, as far as I remember, 512. And here is this one. So what I did, I multiplied my dataset. So I'll open. I did. Sorry. Copy and paste. Copy and paste. And got the data set with 2000 rows. So here it is. The number of rows. Do I have here? No, it's okay. It has much more rows. Of course, I can do it by Python command, but not now. So let's load the bigger data set and start the code again. Run all. So, and what I see that my validation accuracy is increasing. It becomes more and more accurate and becomes 1 and 1, and the plot is similar in this and in that, and I get my numbers. Where is it? Get my numbers. 1, 1, 2, 3, 3, 5, 6, 6, and I also can test some other number that, where is it? Some other number that was not in my data set. I did it myself. Here it is. It was near 7, and it will give me, that is 7. About metrics, accuracy and cross entropy. Accuracy is one of the many metrics in use for measuring success on a classification problem. Accuracy is the ratio of correct predictions, or am I writing to? Yeah? Okay. Predictions to total prediction. Accuracy number correct division total. Okay. There are very many metrics, and on the exam I learned them all. Confusion metrics, true positive, true negatives, and so many. I'll make some other videos about them. A model that always predicted correctly would have an accuracy score of 1. I've got it. All else being equal, accuracy is a reasonable metric to use whenever the classes in the dataset occur with about the same frequency. Okay. The problem with accuracy and most other classification metrics is that it can be used as a loss function, because as GD needs a loss function that changes smoothly, but accuracy, being a ratio of counts, changes in jumps. Okay, so we have to choose a substitute to act as the loss function. This substitute is the cross entropy function. Now I recall that the loss function defines the objective of the network during training. With a regression, our goal was to minimize the distance between the expected outcome and the predicted outcome. We chose Meyer to measure the distance. For classification, what we want instead is a distance between probabilities. Distance between probabilities. Okay, and this is what cross entropy provides. Cross entropy is a sort of measure for the distance from one probability distribution to another. Okay, so my experiment is successful. I did it by myself from the very beginning. I only copied the glass dataset, and the code was wrote by me, but with the help of Kaggle courses and some other and some experience of me and YouTube and Andrei Sazykin and some other guys. Okay, thank you very much for watching. Thank you, Kaggle. You are great. See you in next videos. Bye.